All right, welcome back again, everybody. Today we're going to be doing one of my favorite sections. Actually, maybe the next few sections and then beyond are kind of my favorites. But today we're going to talk about triple integrals. So we're taking our integration process up a dimension, and I even discuss multiple integration later on in this section. So I'm really excited about this one. This one is really fun. This is really what integration is like, in my opinion. So, like everything you've been studying since the end of Calc 1 just starts to come alive in the next like four sections, and then everything in Chapter 16. It's just so fun. Um, Let me pull up the slides and we'll get started. Here we go. Okay, so there's quite a bit to go over. So first, we're going to completely develop the integral mechanics. The good news is that you've seen it a couple of times before, so hopefully by now it kind of sounds, I sound like a broken record. That's a good thing. That's what you want. We're going to define the definite Riemann integral, the definite triple Riemann integral. We're going to talk about Fubini's theorem again, do triple integrals over rectangular regions, triple integrals over bounded regions, changing the order of integration. And this one is a tricky one. So I'll get to it when we get there. But the integral is a scanning machine, and so you have to tell it how to do the scan. And there are six ways when you have a triple integral. So being able to visualize those three-dimensional regions is going to help out a lot when we get to that part of the section. Properties of triple integrals, long story short, they're the same as the ones we saw before. Then we'll talk about multiple integrals and multiple integration. Just frankly, the idea that you can take all of these techniques and take all of these constructions and just go wild with them higher dimensionally. And then we'll finish up just briefly talking about applications of triple integrals. This is really just an extension of what we learned in the previous section to triple integrals, so to regions in space instead of regions in the plane. All right, so oops, that's backward. There we go. There we go. All right, so let's get started. Oop, too far, come back. All right, so first we're going to define a triple integral for functions of three variables. The construction is pretty much the same as what we've seen before. We're going to suppose that we have a function of three variables f that is defined on a rectangular box in space. Maybe we can describe the box like so. It's B, it's the set of all points in R3, where x is between A and B, y is between C and D, and z is between R and S. So that's what you have right here. Okay, we're going to do the same thing we did before. We're going to partition this rectangle B into sub boxes. And remember that if f is integrable, so if everything works out nicely enough, then we can divide those subintervals into we can divide those intervals into subintervals that have the same length respectively. So we could divide AB into intervals x sub I minus 1 comma x sub I of equal width, and then do the same thing for each one of those intervals. So it's like, what is it, like this one, and this one. You can divide those intervals up. And they will each have length delta x, delta y, and delta z, respectively. And then in doing that, we're actually cutting this box up into L times M times N sub boxes. And the sub boxes are labeled B sub I, J, K. And it's literally just one of these tiny little boxes. There you go. So this is a pretty good depiction of what we're doing. Partition the box into a bunch of smaller boxes. Here are the dimensions of the small boxes. So the volume of the small boxes is going to be the product of those dimensions, and so on and so on. So each one of those sub boxes has volume delta V, which is delta X times delta Y times delta Z. Then just like before, we're going to pick a sample point in each one of these sub boxes. The sample point will be this complicated looking thing. Again, don't let the notation freak you out. It's just a sample point in the box. That's all it is. Pick a point, any point in that box, and this is what we're going to call it. It's just, to know which box you're talking about, we need to index things, and the star just indicates that it's a special sample point that you picked. All right, once we've done that, we can define, or we can form the triple Riemann sum. And remember, these are just nested Riemann sums. So if you really needed to, you could think of them as a nesting of three sums. Just rewrite delta V as delta X, delta Y, delta Z. This is us evaluating F at that point and then multiplying by the volume of that box. And then you add all those boxes up and you get like a rough approximation, right? and then taking the limit as L, M, and N, so all three of these go to infinity, we get the definition of a triple Riemann integral. So just for completeness or maybe posterity, I have the complete definition of a triple Riemann integral here. So I'm going to go through it, but it is analogous to what we saw earlier when we learned about double integrals and frankly, single integrals. And it's going to be very similar for multiple integrals. So it's really the same idea. You just want to understand the construction. Let's say we've got a function f defined on a rectangular box. We're going to partition each interval like so. We're going to form a partition of each interval in terms of x, y, and z. And then we're going to partition the box B into these subboxes. Delta x sub I is the length of each one of the subintervals in terms of x. Delta y sub j is the length of the subintervals in terms of y. Delta z sub k is the length of the subintervals in terms of z. This is our special sample point that we're picking in each one of those boxes. And each one of those boxes has volume delta v sub ijk, so you're just taking the product of these things, right? Then we say that the definite triple Riemann integral of f on the box B is the number given that we denote by this. So this is a number, right? This is a definite Riemann integral. This is giving you a number. And that number is defined as this limit. So it's the limit of this triple Riemann sum, but the limit is taken as the maximum of the volumes of the subboxes goes to 0. This integral exists provided the limit exists. Provided that the limit exists for any partition P of the box B, right? If this number is finite, then we can say that the function f is Riemann integrable, and then everything is much nicer. So this is the general definition of a triple Riemann integral, very similar to what we saw before, and we're going to see it again. We're going to see it again. All right, now we can talk about Fubini's theorem. So Fubini's theorem applies to multiple integrals, and it's pretty much the same idea. If f is continuous on a rectangular box, then you can iterate your integration process. So if you wanted to do this triple integral, it is the same thing as doing an iterated integral with respect to each variable. So you would do this integral first, then you would do this integral second with the result of the first, then you would do this integral third with the result of the second. That's what Fubini's theorem lets you do, iterate the integration process. All right, so here we go. Let's evaluate this triple integral of the function xyz squared over this box. And this is one that I want you to try on your own. I think you are all capable of doing this without me showing you first. So think about it for just a moment. Okay. And now say something out loud to yourself. Remember, it doesn't have to be to anybody. It's always nice when someone's hanging out with you to listen to you talk about math stuff, right? But it doesn't have to be to anybody. You can just speak to yourself. Just give your brain that audio feedback. All right. And now try to work it out on your own. You know, thank Fubini. It'll be a nice, it shouldn't be too bad to compute. Go for it, and we'll do it together in just a moment. All right, here we go. So first thing I want to point out is that this function is continuous. Why is it continuous? Let me ask you, why is it continuous? It's a polynomial. So it's a polynomial in 3 variables, which is continuous on the entire space, R3. So it's certainly continuous on this box B. And since this box B is a 3-dimensional rectangle, Fubini's theorem says that we can integrate it iteratively, and we could even change the order willy-nilly, and we would still get the same result. So we're going to do it iteratively. I'm going to integrate with respect to x, then y, then z. Why? Just because. It's a rectangle, and Fubini's theorem says you could iterate in any order you want, so your choice, whichever one you want to do first. I did x first, and then y, then z. So here's me applying FTC2 in terms of x. Simplify this to get this. Now I'm going to apply FTC2 again to the y term, the y variable. You get this. Simplify this, and you get that. And then last but not least, we run FTC2 one more time with respect to z, and we get 27 over 4. So that is what that triple integral is. Just as a reminder, oh wait, do I say it right here? Hold on. I say it somewhere in here? I'll say it again later on, but just as a reminder, yeah, I don't think I've said it yet. When you're performing this integration process, you should be losing a variable at every step. So what I mean is if you integrate with respect to x, then x should no longer appear after you've applied FTC2, for example, right? So if you go through one of these processes, like one of these steps involving FTC2, and you still have an x, something has gone wrong, guaranteed. You should be losing a variable at every step of the integration process. All right. So now that we've seen how to do it over rectangles, how do we do it over general regions? Well, the idea is the same as what we saw before. We're going to, if we have a bounded region E that we want to integrate over, we're going to contain E in a box B. We're going to construct a function capital F using the indicator function. Remember, the indicator function just says you're zero if you're not in the set. That's it. So that has the effect of zeroing out our integral or zeroing out this function when we're not on E. So that's like the trick to getting around the fact that Fubini only applies to rectangles, right? That the iterated integration process only applies to rectangles. So once you have gone through this process, you can actually define the integral over E, the triple integral, as the integral over B of this function. And this integral will always exist as long as f is continuous and the boundary is sufficiently smooth. We'll just say that, sufficiently smooth. So where things get a little more interesting or maybe a little more difficult is when the boundary of these regions are not nice, maybe fractal in nature. So that makes things a little bit more complicated because, well, I won't get into it here, but you have to be much more careful with the way the integration is going to work because that's exactly when things start getting kind of wild. All right, so assuming in this class that things are nice, assuming that the boundary of our regions are sufficiently smooth, right? Then we can start to define these region types and we can iterate our integration and so on and so on. So we're going to assume niceness for right now. um, Oh yeah, so now we're going to talk about the different types of regions. Once again, you do not need to memorize these type numbers. So I'm not looking for you to be like, oh, that's a type 1, oh, that's a type 2, oh, that's a type 3. If you do happen to remember them, great, it's not going to hurt. But you don't need to memorize the types. You just need to understand how to integrate depending on what these regions look like. So that being said, a type 1 region in space in R3 is a region E that is bounded by two surfaces in terms of X and Y. So that's what you're seeing here. So this region E is a type 1 region. And yeah, it is a type 1 region. And basically it's bounded between two surfaces that are defined as functions of X and Y. All right, that's a type 1. Now, by Fubini's theorem, we can iterate this integration process. So we can actually write it as a double integral and a single integral. We're just going to integrate first in between the lower bound, the lower bounding surface, and the upper bounding surface. So our scan is going to go this way first. Ooh, maybe I shouldn't say that. This way first. Scan that way. Okay. Then we have to tell the integral how to scan in the other two dimensions. So if your projection, so if the projection of your region E down here, we'll call it D, if that can be described as a type 1 planar region, then this allows you to continue to iterate the integration process. Again, you don't need to remember what is type 1, type 2, yada, yada, yada. But what we're saying now is if your region is actually defined as being bounded between these two surfaces, and then the sides are bounded between two curves. So these are the two curves right here. And then the remaining side is bounded between two numbers, I'll say. Then you can completely iterate the integration process. So this is what Fubini's theorem lets you do. All right, so this is one where I actually want you to stare at it and think about it for a moment. So look at this figure, look at what this is saying, and make sense of how the scanning would look in your head. Try to imagine almost an animation of the scanning process in your head, okay? Okay, Now, a couple of notes about this process. I've kind of already said these, so this won't take too long. Fubini's theorem is what allows us to integrate iteratively like before, so that's why we like Fubini's theorem. Um, for triple integrals, the first pass of the scan has to be between surfaces in some way. It could be left, right, forward, back, up, down, but you're going to integrate between two surfaces first. Then the second scan is hopefully between two curves, and then the last pass is between two numbers. So try to keep that idea in mind. That's really what we're doing. Go between surfaces, go between curves, and then go between numbers at the end. And that should be the complete scan. This is what I said before. This is what I was thinking of earlier. Um, After each integration that you perform, the number of variables should decrease by 1, and the remaining variables should be only those that are indicated by the remaining differentials. So, like I mentioned earlier, if you integrate with respect to x, but then after that process, you still have x in your integrand, then you've made a mistake, guaranteed. So, go back, check your work, and then proceed once you find the error. All right, so next, another type of region. So what is a type 2? Sorry. Still type 1 region. So if the projection of your region E to the xy plane is a type 2 planar region, then this is just saying you can scan between two curves in terms of y instead of x. That's all. That's all this is saying. And then you can go between two numbers, c and d. And when you do that, you get this. So again, between two surfaces, in terms of x and y, we'll say, and then between two curves, in this case, they're in terms of y instead of x, and then between two numbers. Yeah, so don't memorize all this stuff, just practice integrating and doing multiple integration and think about how the scan goes, all right? Okay. Okay, so here's one. Let me see. Actually, this is a good one for you to try to do on your own too. So I'll read it out loud, give you a moment to think about it. Evaluate this triple integral, but now E is the solid tetrahedron bounded by these four planes, x equals 0, y equals 0, z equals 0, that's not too bad, and then this plane right here. So think about this one for just a minute, right? And then now say something out loud to yourself or to your friend or to your colleague about what you would try first, maybe. Right? And now try to work it out on your own. One hint that I will give you about this is it really, really does help if you can visualize in 3D what these objects look like. So what I'm hoping is that by this point in the course, you're able to see what these restricting planes kind of look like, all right? If not, remember, you can always go to Mathematica, you can go to Desmos and get a picture of them. But at this phase, you really want to try to have a good visual understanding of what's going on. It will help you out immensely, okay? So try it on your own, and we're going to do it together in just a second here. Right. All right, here we go. So this is exactly what I just said. So visualizing the object in 3D is an essential skill, yada, yada, yada. It can also help if you want to draw projections of the region onto the appropriate coordinate planes. We'll see that a little bit later in the slides too. In this example, we're going to use the XY plane. So here's what it looks like. This is the tetrahedron, right? It's bounded by those three coordinate planes. Those are the coordinate planes, respectively. And then it's bounded by this plane right here, which is like this, the angled one that you're looking at, right? There you go. All right, so here is the fun part. You want to integrate over this region. You're going to integrate this function over that region. The function is just z, not too bad. That function is continuous. It's continuous because it's a polynomial, so it's continuous everywhere. So that means it's certainly continuous on this region, which means that Fubini's theorem says you can iterate your integration process. So you need to pass between two surfaces, then you need to pass between two curves, and then you need to pass between two numbers. That's really the idea. So imagine in your head how you want to scan the region. And see, I have it on the next slide. Yeah, I have it on the next slide, but I'm going to use this picture for just a minute. If I wanted to scan between two surfaces, we might as well just integrate with respect to z first. So I will scan from down here to up here, wherever this this plane is, right? So z, we're going to say, goes from 0 to 1 minus x minus y, right? Now that we've scanned between two surfaces, we need to scan between two curves, and that's where this picture can help out, right? So if we project this down onto the xy plane, this is what we see. So this triangle that you're seeing here is this triangle that you're seeing here. There we go. Great. So we've basically, I can't show you, but imagine like my pen coming up out of the screen and going down into the screen right here, right? So we've gotten the vertical scan done. Now how are we going to let y scan? We'll do with respect to y next, right? So y is going to go from 0 to this line, but this is the line 1 minus x. So y is going to scan in this direction, right? Do that. And then the very, very last scan will be to go from 0 to 1 in terms of x. Okay, that's the scanning process. Here's what it looks like as an iterated integral, right there. This is a general description of the region E. It's the set of all points in 3 space, where x is between 0 and 1, y is between 0 and 1 minus x, and z is between 0 and 1 minus x minus y. All right. Here is the iteration. It's exactly like I was saying a minute ago. We do z, then y, then x. Z goes between 0 and that plane. Y goes between 0 and that line. And x goes between 0 and 1. Nice, huh? That's all it's doing. All right, let's do it. The integration part is like the like the algorithmic part almost, right? So here we go. We're just going to apply FTC2 3 times. First, with respect to z, we get this. Apply it, simplify it. Now we have a function that is only in terms of x and y. That's a good sign. We've done things well. Now we're going to apply FTC2 again with respect to y. Apply it, simplify, you get this. Now notice the integral is just a single integral. So we've already accounted for the other 2 dimensions of the scan at this point. This is all that's left. FTC2 one more time, you get this. Apply it, simplify, and last but not least, the answer is 1 over 24. So that is the integral of this function over that tetrahedron. Right. Okay, so next there are some other regions. So I have them here just for completeness and posterity. I'm not going to dwell on them too much. All I can say is when you are performing these integrations, just remember you're scanning a region and you have to figure out how to scan it in an effective way. So here the book defines a type 2 region in space as a region that lies between the graphs of 2 continuous functions of y and z. So in other words, your surfaces are here and back here. They call that a type 2 region, all right? Fubini's theorem lets you integrate iteratively. There you go. A type 3 region is similar, except now your surfaces are in terms of x and z, right? So I should say x and z. There you go. So really all they're saying is you could scan vertically, and we would call that a type 1 region, or you could scan in terms of, what is it? Lost my train of thought. Where did it go? Oh, yeah, exactly. You could scan like, oh my gosh, this way. That kind of works. Or you could scan this way. There we go. It just depends on the region. So that's the thing. It depends on the region, right? So you have to be the one to figure out which region is going to be like what region your what type your region actually is. So it can get very confusing if you're thinking of the numbers of the types, but you'll get lots of practice. All right, here we go. Yes. Yes. Okay, this is a good one for you to think about, and then we'll do it together. Try to evaluate this integral here, where E is the region bounded by the paraboloid y equals x squared plus z squared, and the plane y equals 4. So here is one where I want you to try to imagine and sketch the region, and then I want you to imagine how you would scan that region, all right? And if you can find an effective way of scanning the region that you think would be nice, then try to evaluate the integral. All right, so let me throw up the thinker. Think about it for a minute. All right, now say something out loud to give your brain that audio feedback to help you make sense of the problem. And now try to work it out on your own. At least try to visualize and sketch the region and think about how you would scan it. All right? And we'll do it together in a moment. All right, here we go. So the region bounded by this paraboloid and the plane y equals 4. So this is what a sketch would look like. So this is what the region is. It makes sense. It's one of those quadric surfaces that we saw back in 12.6. There's the paraboloid, and we're basically cutting it off when y equals 4. All right, so now here is where you have to start to make some decisions. You have to think about how you would scan that region in the most effective way so that your integration process would be simple. I'll just say it like that. Here's the function you're trying to integrate, and this is the region you're trying to scan. So we have options here. We could view it as a type 1 region where this is this is how it looks. Wait, do I have this written right? Yes, exactly. So yeah, exactly. So what we could do first is we could think about projecting this object down to the XY plane. And if we were to do that, this is what the projection would look like. So I can't do it, but imagine you were like above it looking down, right? That's that's what we're doing. And if you were above it looking down, this is what you would see. All right. So this is one way that you could think about scanning it. You could scan it between these two surfaces. And then you can choose how you want to scan this region here. Maybe you could go from here to here, and then you could go from here to here, right? So if we were to do it that way, this is the way that our iterated integral would look. And this immediately, this is where you should almost feel like like a minor twinge, like a sense of dread, because you're like, oh my gosh, how am I going to integrate this with respect to z? And then these are my bounds, and how messy is it going to be? I'm not trying to say that it is impossible to do. It's likely possible, but feels like there should be an easier way to do it. So maybe what we need to do is we need to rethink the way that we're scanning our region, and then maybe there's a more effective way of scanning it. Here we go. Let's think about it as a type 3 region, a type 3 region. So in this case, what we do is we project onto the XZ plane, and then what we're going to do is we're going to get a disk of radius 2 centered at the origin, and then we're going to have as the left boundary our paraboloid, and the right boundary just the plane y equals 4. So here's what it looks like. There we go. So rather than scanning this way first, what we're going to do instead is we're going to scan this way first, which isn't such a bad idea, right? Because we could easily see like how to scan between here and here, here and here. Oh, that's not so bad. I need to integrate between the actual surface of the paraboloid and then this plane. And then I just need to think about how I'm going to scan that circle, that disk that remains. So this is the projection onto the XZ plane. So if you took this and you projected it onto the XZ plane, this is what you would see. Not too bad. Now you get to make a choice. How would you scan this region? There's a couple of ways to do it. I mean, we could just scan from here to here, but maybe you can think of a more effective way of scanning such a radial region. Wink, wink, wink. Okay, so here's what we have. Before we start talking about scanning the region, the planar region, D3, this is what we have so far. So we're going to first scan in the y direction. We're going to scan from the paraboloid to the plane y equals 4. And then we'll deal with the other bit in just a minute here. So right away, this is what we have. And one thing that's nice about this particular scan is that this function here does not depend on y. So it's really, really easy to integrate with respect to y. You're just going to get y times this thing. And then you evaluate it at the upper bounds and then take the difference, right? Upper and lower bounds and take the difference. So you get this. This is after applying FTC2 with respect to y right here. And then you get that. Okay, now we're basically back to the problem of scanning this region here. How do you want to scan it? You have choices. You could go left to right first. You could go top to bottom first. Or we could convert to polar coordinates. because that region is very, very conveniently described in terms of polar coordinates. So we might as well use polar coordinates to our advantage, express it in terms of polar coordinates, and then iterate the integration like so. Here we go. Um, Again, these are continuous functions. They're continuous in basically everywhere. So we can iterate our integration. Here we go. How do I describe D3? Well, we're going to do a change of variable. We're going to convert to polar coordinates. X squared minus z squared. Oh yeah, we're going to let x be r cosine theta and z be r sine theta, right? Because we're on, right, x and z. So x is r cosine and z is r sine. There we go. All right, so now how do we describe the region? Well, r goes from 0 to 2 because that's the radius of the disk. And then theta goes from 0 to 2 pi because we're doing the full rotation. Wait, did I do that right? No, backward. There we go. All right. Again, good news. This function doesn't depend on theta, so we can actually split this into a product of two integrals. Integral with respect to theta, integral with respect to r. Apply FTC2 twice. There's when we apply it with respect to theta. Here's when we apply it with respect to r, and then simplify to get 128 pi over 15. Boom, that's it. So how fun is that? You know, you get to like choose how to scan the region and all that stuff. And on that note, we need to talk about changing the order of integration. So like we did with double integrals, it can be very, very helpful to change the order of integration, as we just saw a second ago, right? However, when we change the order of integration, we have to re-explain to the integral how to scan the region. And this can be difficult if you're not comfortable with 3D visualization yet. The other thing I want to remind you of is that Fubini's theorem says that it doesn't matter what order you integrate on a rectangle, right? So if you just want to integrate over a rectangle, it doesn't matter what order you do the integration in. You can swap everything around willy-nilly, no changes, everything works. If you're not integrating over a rectangle, then you have to be more precise, and you have to quite literally tell the integral exactly how to scan. And how it scans changes completely when you change the order of integration. So do not make the mistake of just swapping the order and not changing any of the bounds. You have to change the bounds when you swap the order of integration. For a triple integral, there's actually 3 factorial or 6 different ways that you can iterate the integration. And we're going to practice switching it for just 2 ways right now. Here we go. So here is an iterated integral, a triple integral, right? And so what I want you to try is I want you to first express this iterated integral as a single triple integral, and then try to reorder the iterated integration in these 2 different ways. First, integrate with respect to x, then z, then y. And then part B, integrate with respect to y, then x, then z. All right? So here's one I want you to try on your own first. So think about it for just a minute. Okay, now say something out loud about how you would begin. What would you do first? Okay, and now try to work it out on your own, and we'll do it together. My suggestion is take a look at these upper and lower bounds and try to imagine or draw a sketch of what the region would look like, and then think about how you would scan it. Okay, here we go. So the first thing said to frankly, just write this as a triple integral over a region. That's not so bad. That's not so bad. We can rewrite this iterated integral as a triple integral over the region E, where E is described as this region. So X is going between 0 and 1. Y is going between 0 and x squared. Z is going between 0 and y. There we go. So that is what the region looks like. This is a description of the region itself. Now we get to change the way that we scan the region. And when we do that, it's going to change these inequalities. It's going to change these representations of like the bounding curves. That's really what it is. So here we go. This is what the region E looks like. So if you can get a sketch of the region, or if you can visualize it in your head, it will help out a lot. But this is just kind of literally converting this into a picture. So maybe I'll start with surfaces with respect, or a z surface, and then y curves, and then x numbers. I'll do it in that kind of intuitive way. So notice z is going between 0 and y. So the plane z equals 0 is the xy plane. And the plane z equals y is this diagonal plane right here. Oops. It's hard to sketch. All right, so z is going from here to there. Now, what is y doing? Y is going between this curve, I'm sorry, y is going between this line and this curve, y equals x squared. Okay? And then lastly, x is going to go between 0 and 1, and that's how we describe our region E. So it's literally like you can slice space into this region between two planes, and then you can slice that region as the region that will go between these two curves, and then you can add up in terms of x. So these are the projections onto the different coordinate axes. This can help you visualize the scan. I personally find that it is easier to think about it in terms of like a 3D picture, but there's all these different ways you can scan it. The one thing I will remind you of is after each scan, you should be losing one variable. So keep that in mind. If you want to scan with respect to z first, then your remaining variables should be x and y. If you want to scan with respect to y first, then your remaining variables should be x and z, and so on and so on. So keep that in mind to help guide you. Here we go. Part A asked us to integrate with respect to x first, then z, then y. All right. So what we want is we want our variable x to pass between two surfaces. Then we want z to pass between two curves. And then we want y to pass between two numbers. So we get this. Oops, this right here. Okay, let's make sense of this decomposition. Let's make sense of this iteration. So we're integrating with respect to x first, okay? So like this stuff. Now, what does x go between? So x is going to go between, what is it, this and this, all right? But not that curve. What I mean is that surface, So it's going to be almost like a cylinder right here, right? And then another plane right here, okay? So we're passing like so. What is the description of this surface in terms of y's or z's? It's square root of y, right? Because this curve right here is y equals x squared. So that means that x equals root y. And we're only taking the positive one because we're not doing the negative version, so just the positive one. And we're going to go from this edge of a cylinder to this plane that you see right here. Oops. And that's where we're getting these numbers, or these bounds, these lower and upper bounds. There we go. So now we have sliced space a little bit. All right, now what happens? So let me back this up. Right? Okay, so now what happens is we need to integrate with respect to z. So what does z go between? Well, let's see. Z goes between, well, it's going to go between down here and up here, right? So it's going to go between 0 and y, 0 and y, and that's where we're getting this. Let me go back to the projections for just a minute so you can see what z is doing. So z right here, there we go, this one. So it's going to go from here to here. That's what we're saying. Z equals 0 to z equals y. That's how z is like passing between those. There we go. And then last but not least, we want to integrate with respect to y. Y is just going to go between 0 and 1. So here to, here to here. That's one way to scan the region. Okay, now let's scan it in a different way. That is just one way to scan it. And who knows, maybe by scanning it in this way, it makes the integration of your function, which we don't know for this problem, maybe it makes it easier. That's the moral of the story. Now let's scan it in a different way. We're going to integrate first with respect to y, then x, and then z. So we're going to scan y between two surfaces. So here's y. So what is y going to go between? Well, y is going to go between this plane right here and then this cylinder right here. So it's kind of hard to see, but because you can't like, you know, yeah, this is why you need to play with it like earlier on in the course, like with physical manipulatives or with Mathematica or Desmos, because you got to be able to like turn these things in your head to see what it looks like. There you go. So what I'm trying to do is I'm trying to look at it almost from the side here just to see what's happening. So y is going to go between here and this curve. So that's where we're getting z and x squared. So y is going between z and x squared. All right, now what's left? So we went between here and here. Now we're going to integrate with respect to x next. So what does x have to do? Okay, well, okay, so then x is going to need to go between this curve and this wall right here. Something doesn't seem right though, because when I think about scanning from this curve to this curve is in terms of x's and y's, but I already integrated with respect to y, so I shouldn't have y's involved, right? So let me think more carefully about this. What is x going between? Oh, look, okay. Ah, I see, I see. Yes, yes. Okay, so I don't know if you can kind of see it here, but this little curve right here, this is affecting the scan. So we're going to scan from this little curve here to the wall here. And what is the equation of this little curve? Well, this little curve is going to be, what is that? That's z equals x squared, this curve right here. So we're going to integrate from square root of z to 1, if I'm not mistaken. Let me check. Okay, let's go back and look at the projections. Yeah, yes, yes, yeah, exactly. So now what I'm visualizing is this. I'm thinking of this, and we need to basically go from here to here. That's the scan that we're doing. But in this case, since z equals x squared, we get x equals root z. So we're going to scan from this curve to this line, and that's where we're getting these bounds. All right. Now this can be tricky, so give yourself time to process it. Make sure you're doing the homework. Make sure you're visualizing these objects somehow using Mathematica or using Desmos or something so that you can get intuition for how these things look, all right? All right, last but not least, now that we've integrated with respect to y and x, we integrate with respect to z, and z is just going to go from 0 to 1. There we go. And that's it. All right, fun stuff. It's a tricky example, but it's a good one to make sense of. Okay, so now, actually, let me see. Oh, yeah, yeah, nice. So now we're going to talk about some properties of the triple integral. Good news is the properties are the same ones that you saw before. So here we go. First, we have linearity of the triple integral. The multiple Riemann integral is linear. So these properties just hold for any number of variable integrals. So if you wanted to do the triple integral of a sum or a difference, that is equal to or the same as doing an integral of the first term and then adding or subtracting the integral of the second term. So integral of a sum or difference is a sum or difference of integrals. Yay, everybody loves that. Then there is constant multiples. Because the integral is linear, you can pull constant multiples out. Good stuff, good stuff. What's next? Monotonicity. So this is one we saw with double integrals. We're seeing it again with triple integrals. Actually, you saw it with single integrals too, back in Calc 1, and it holds for multiple integrals as well. So if your functions have this order relationship where f dominates g, then the integral of f has to dominate the integral of g. So whatever this number is, it's going to be bigger than this number because this value is always bigger than this value. There you go. Similarly, if the order is reversed, right? So if f is always below g, then this number is always going to be less than or equal to this number. Same idea. Monotonicity. Um, Finite additivity. So once again, if you can decompose your region E into two disjoint regions, disjoint, but they are allowed to overlap over the boundary, then you can say that the integral over the entire region is equal to the sum of the integrals over the sub-regions. That's it. It doesn't matter if they overlap at the boundary because in this case, the three-dimensional integral of a surface is zero. Kind of the same way as the area of a curve is zero, right? Area of like a line is zero. So it's the same thing there. It doesn't matter if the boundaries overlap because the integral will just be zero if we're doing a triple integral. Then there is a volume formula. This is always super handy because if you need to compute lengths or areas or volumes or hypervolumes, this is how you do it. You literally just integrate the unit function, which really just amounts to adding up all of the change, the infinitesimal change in volume, and adding up all of the infinitesimal change in volume gives you the exact volume, as long as your region is the boundary is sufficiently smooth, and that gives you the volume. Same thing for higher dimensions. If you want to know the hypervolume, just do the quadruple, quintuple integral of d, whatever you want to call it. Okay, then there's boundedness. So we saw this one for the single variable integral and the double variable integral. Now we see it for the triple variable integral, and it keeps going on and on and on. So if your function f, scalar function, is bounded between little m and capital M, then the integral of f over the region E has to be bounded between little m times the volume of E and capital M times the volume of E. That's it. Boundedness. All right. Now, all this being said, here's the fun part. I know I've been saying it. We might as well just lay it out and write it out and make it clear. All of this stuff extends to higher dimensions. So we can perform integration in any number of dimensions and any number of variables, and the construction of the Riemann integral is analogous to what we've seen already. So hopefully you are very comfortable with that construction and the mechanics of the Riemann integral, because now you get it for free for the rest. Like it's pretty much the same. So we'll go through it, and then you have it forevermore. If we're given a continuous function f of n variables, and it's defined on some bounded region omega in Rn, that's n-dimensional space. First, we're going to contain omega in a hyperrectangle R, and we're going to define our function f using an indicator function. Again, indicator function just means that this function is 0 off of the region and 1 on the region. This lets us do our integration, right? We partition the hyperrectangle into a bunch of hyper subrectangles. We choose a sample point in each one of these hyper subrectangles. We evaluate the function at the point in these hyper subrectangles. We can say that each hyper subrectangle has hypervolume delta V sub I, and then we can construct our Riemann sum, just like you saw before. There it is. Evaluate the function, multiply by delta V. That's it. Because of the indicator function, this really just becomes this, right? And this should say then. There we go. Then we say the function f is Riemann integrable if for any partition of your hyperrectangle, this sum exists, meaning it's finite. Sorry, that the limit of those sums exists and is finite. And then we write the definite Riemann integral as this. All right. So the moral of this story is everything that you saw previously still applies in higher dimensions and with more variables. Really, we're just taking the limit as the hypervolume of these sub-hyperrectangles goes to 0. And if that number is finite, then we can actually define the multiple Riemann integral, right? This d to the n is just kind of indicating how many differentials you have in this process, because we don't know, right? It's n, it's arbitrary. But this is kind of how we denote it if you want it to be a bit messy. But honestly, typically, when the context is understood, we just write this. we just write this and we stop saying hyper for everything. It's like if we're working in higher dimensions, we get that things are hyper. So um, a lot of times this will just indicate that you're doing, sorry, this will just indicate that you're doing an integral in multiple variables. But usually before you get to this point, we'll say we're working in n-dimensional space, and then x is a point with n coordinates, yada, yada, yada. This is why you write sentences. This is why you make things clear. And not everything just needs to be like a bunch of equations written around. Just be precise, be specific, write out what you're doing, and people will understand it. That's the goal. Um, okay, so the takeaway from all this is I want you to understand that the technique of integration is a very general one. It does not need to be restricted by dimension. It does not need to be restricted by physical interpretation. So this might feel kind of weird, but just because we use physical interpretations to gain intuition for these ideas does not mean that that is the extent of this mathematical theory. The beauty of mathematics, in my opinion, one of the beauties is that it doesn't have to rely on something physical or something real or something realistic. It lets you touch your imagination in a precise way. And that's what's so awesome about it. So I want you to take that away from this as well. Um, yeah, also keep in mind, many mathematical and scientific concerns involve data sets that have hundreds of variables or equivalently hundreds of dimensions. And what I'm trying to say is that we can integrate functions of these variables. It doesn't matter how many you got. You just need to have appropriate conditions to define an integral. That's it. Continuity is a great one. Continuity and smoothness of boundary. Once you've got that, everything is nice. Everything is comfortable. Um, so another takeaway here, understanding the mechanics of the Riemann integral and ultimately a little bit of measure theory, that's what enables us to make sense of these non-physical, high-dimensional mathematical constructions. And the formal definition of a limit is what allows us to assert the validity of such constructions. So even though we may not be able to visualize or make intuitive sense of very high dimensional objects, we don't need to because we have the mathematics, and the mathematics will guide us when our intuition fails. That's another reason I like it so much. So what's exciting for me is that in the next two sections, we're going to modify the mechanics of the Riemann integral again in two different ways. And then in the last section of this chapter, 15.9, we're going to see like a general version of that modification. And you've actually seen it since Calc 1, but only in very specific particular ways. We'll generalize it in 15.9. So all that being said, now let's return to triple integrals for a minute. And we're going to extend the physical applications that we saw in the previous section to 3 dimensions. I won't spend a ton of time on it. It's really just a natural extension, and you'll get to practice it in the homework and on the activity. So here we go. All the stuff we learned in the previous section applies. So for example, we can have a density function that is in terms of 3 variables. Very common, right? You want to talk about the density of this point in space. We can do that. Then the mass of this region, if there's a region we're interested in, is literally just adding up the densities, right? Density times the infinitesimal volume of one of those little sub boxes. So that's the total mass, density times volume again. Now you can talk about moments about the 3 coordinate planes, and the construction is equivalent to the moments that we saw before. So if I want to know the moment with respect to the YZ plane, then I take the distance from the point to the YZ plane, which is x, and then multiply it by the density, right? So remember, have this picture in mind. Always want to have these pictures in mind, right? So this is y, this is x, this is z. Here's my point in space, okay? If I want to know the moment of this region with respect to the YZ plane, I need the distance from that point to the YZ plane, which is going to be in terms of x. There it is. If I want the moment with respect to the XZ plane, that's over here, then the distance is going to be y. If I want the moment with respect to the XY plane, which is this one, then the distance is going to be z. And that's it. Natural extension, right? Again, if you memorize the previous formulas, the previous formulas for the moments with respect to the axes, you already understand the construction. So you already understand how to get this for free. Fun stuff. Oh yeah, and then what is the center of mass? Well, the coordinates of the center of mass are x, y, z bar, and you just do moment divided by mass, moment divided by mass, moment divided by mass. And that's it. All right. Similarly, you can get the moments of inertia. So the moments, the moments of inertia about the three coordinate axes are given by this. I sub x is equal to this. Again, because you're basically going to the x-axis. So if you're going to the x-axis, your distance is going to be in terms of y squared and z squared, right? It's like the distance to, almost think of here, almost think of the x-axis as, right? It's like, I don't know, almost like if you could imagine this, like how do you get, what's the distance from there to the x-axis? Y squared plus z squared, square root, right? That's what's happening here, right here. And then you do the same thing for moment of inertia about the y-axis, moment of inertia about the z-axis. Those are all just the same. And they're squared, right? So remember the moments of inertia are where you have a square, right? Because you're squaring the distance. There you go. All right, so on that note, let's play. That's the end. We'll do a couple application problems in activity. You'll have a couple application problems on the homework. I won't ramble too much longer. The next section is all about cylindrical coordinates, right? Cylindrical, yes, cylindrical coordinates. Okay, next few sections are fun. All right, so I'll end here. Thank you again for watching and listening, and I will see you next time.